slope fields defined by functions, as the one shown here in this picture, can be used to approximate graphs of antiderivatives of these functions. Such approximations are formed simply by connecting the arrows of a slope field together. This is a special case of a general method of Euler to approximate numerically solutions to differential equations. In this video, I discuss slope fields from the point of view of an example. By elementary functions, we mean functions defined by expressions involving polynomials, rational functions, trigonometric functions, exponential functions, or their inverses. These are the functions that we see in calculus all the time. The derivative of an elementary function can be computed easily because differentiation is completely rule-based, and the derivative of an elementary function is also an elementary function. Furthermore, they usually are of the same type. That is, the derivative of a polynomial is a polynomial, the derivative of a rational function is a rational function, and the derivative of trigonometric and exponential functions are of the same type as well. There are many elementary functions whose antiderivatives are not elementary. That is, there are functions for which we know that they do have antiderivatives, but that these antiderivatives cannot be expressed in terms of functions that we already know. Examples of such functions are either negative x squared, a function which is very important in statistics, sine of x divided by x, a function which is important in optics, and then a function which is of the type 1 divided by square root of a polynomial, if this polynomial is of higher degree. This is a function which is needed when, for example, building models for hard disks for computers. So all these functions have important practical applications, and they share the common property that their antiderivatives cannot be expressed as elementary functions. They are not elementary functions. So when we have to compute with antiderivatives of these functions, we need to resort to numerical methods. And the simplest most such method is provided by the slope fields. So for an antiderivative of a function, small case f, we have that the antiderivative capital case F has the property that capital case F prime equals small case f. So if capital case F is one antiderivative, then we may add any constant to capital case F to obtain yet another antiderivative. This means that the graphs of the antiderivatives of a function fill the whole plane. And they have the property that capital F prime equals small case f. So we may approximate an antiderivative through a given point x0, y0 by a slope field of f. And the slope field is formed by drawing small arrows whose slope is given by this function small case f. I will discuss that next in an example. Consider the task of sketching the slope field defined by the function y equals x squared minus 1. Using that slope field, we then sketch the graph of that antiderivative of the function y equals x squared minus 1, whose graph passes through the point 1, 1.5. We perform the following steps. First, we select the viewing rectangle. The point that we are interested in is the point 1, 1.5. Therefore, we select a viewing rectangle centered around that point. This particular viewing rectangle shown here, the x-coordinates range from -1 to 3, and the y-coordinates range from 0 to 2.5. Then we form a grid covering that viewing rectangle, and on these grid points we perform computations. On the grid points we are going to place arrows, and the slopes of these arrows are determined by the values of this function that we are computing with, that is in this case the function y equals x squared minus 1. So to this end we first form a table of the values of the function x squared minus 1 corresponding to the x-coordinates of the grid points. The x-coordinates of the grid points were -1, -0.5, 0, 0.5, 1, 1.5, 2, 2.5 and 3. And the values of the function at these points have been computed, and the values are in this table. Here we have our viewing rectangle with the grid and the point of interest indicated by the blue star. We form the slope field simply by first computing the slopes, that is the values of the function. We computed those already on the previous table. The function was x squared minus 1. Its values, that is the slope of the slope grid arrows that we will eventually draw, is 0 if x equals -1. If x equals -0.5, the slope is -0.75. If x equals 0, then x squared minus 1 is -1. Therefore the slope is -1. If x equals 0, if x equals 0.5, the slope is -0.75. If x equals 1, the slope is 0. If x equals 1.5, the slope is 1.25, and so on. So next we draw these arrows on the grid points, and the slope of the arrow is given by the value of the function x squared minus 1, that is by the rightmost column of this table. So when x equals -1, the slope is 0. Therefore, for all grid points lying over x equals -1, we place a horizontal short arrow. For all grid points lying over x equals -0.5, we place an arrow that points down because its slopes are -0.75. If x equals 0, then the slope is even steeper, -1. Therefore the arrows point down as indicated here in this picture. If x equals 0.5, the slopes are again -0.75, and if x equals 1, the slopes are 0. Therefore here we have horizontal arrows again. And if x equals 1.5, then the slopes, that is the numbers x squared minus 1, that results to 1.25, and the slopes now point up, and as x increases, the slopes start pointing up more and more steeply. So this is the slope field of this function y equals x squared minus 1. Let us take a little bit closer look at the slope field, and now I delete the grid because we do not need it anymore. So we have the slope field arrows, and to get an approximation of an antiderivative of this function x squared minus 1, we simply connect these arrows and form this green curve. So this green curve is the graph, or rather an approximation of this graph of an antiderivative of the function x squared minus 1 that passes through the point 1, 1.5. So if I now even delete the slope arrows, then we are left with our approximation for the antiderivative of this particular function. For many functions, this kind of a numeric way of approximating antiderivatives may be the only way to compute values of antiderivatives. It is clear that as we take more grid points, as the grid gets denser, the approximations also get better. But these are always only approximations. This method of approximating antiderivatives of functions is a special case of a more general method to approximate solutions to differential equations. This method is due to Leonhard Euler, a Swiss mathematician, one of the greatest mathematical minds of all times. He was born on 15th of April in 1707 and he passed away on the 18th of September in 1783. Here you see a portrait of Euler and a picture of an old Swiss banknote honoring Euler. Euler was born in Switzerland and he moved to St. Petersburg on the invitation of Peter the Great and then back to Berlin where he spent the rest of his life.